Hello, good morning, Lamuel. Benson, good morning, Mlenga, Chichi B, good morning. Okay, so I'm just trying to write a list of everything that we'll be handling today. Power trigonometric integration, then we can talk about U substitution, and then we can talk about integration by parts. Okay, good morning, Dismas. So good morning, everyone. Good morning, Evento. Good morning, Miriam. Okay, hopefully everyone is okay. Let's see what can be covered in today's session. Okay, so hopefully you guys are watching each and every video, and hopefully you guys have gone through each and every document that we've sent. Aaron, good morning. And even as you learn new things, please start revising the old, okay? Start revising, because you may think you still remember something, but when it's actually brought to you, you find yourself struggling. Not because you don't know, but because you may have mixed one or two concepts up. So revisions are equally important. Okay, so when we have 50 people viewing, we will start. Okay, so today we'll be doing calculus part 1. We did the introductory part, and now we're going to continue and hopefully do a little bit of integration. Normally, this is a topic that would take a whole month to cover, but we'll try and compress things so that in a few sessions, at least we do the basics, okay? So we need to make sure the basics are covered so that you guys stand on solid ground, and then bit by bit we begin polishing up. So it's going to be a very, very interesting session. So calculus part 2, we are going to look at the chain rule. We are going to look at implicit differentiation. Implicit differentiation is hot. This one is hot. Okay. Implicit differentiation is very, 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 very hot. So make sure you understand these things. Okay. So we can start. We can start. So we're going to look at chain rule. Chain rule. What is chain rule? Okay, so we use this when one part of a function, it's hot. We use this when one part of a function, has been raised to a relatively large power. Okay. And then for chain rule, the key thing is identify U. Identify U. How do you identify U? So U is the item that has been raised to that large power. Okay, so that's the key thing. And then the formula for chain rule is dy over dx is equal to dy over du times du over dx. You get? Meaning differentiate y with respect to u, and then differentiate u with respect to x, and then multiply the two answers that you get. For instance, you can be given a function to say y is equal to 5, 2x minus 5, everything to the power 10. Okay, and then they will tell you to say find dy over dx, meaning they want you to find the derivative of this whole thing. Okay, they want you to find the derivative of this whole thing. So we said we use chain rule when one part of a function has been raised to a relatively large power. So if you look at this function, we have 2x minus 5 being raised to the power 10. Okay. So identify u. Whenever you notice that one part of a function has been raised to a large power, identify u. What is u? U is the item that has been raised to that large power. Now, careful. U is not the whole thing that has been raised. U is the item that has been raised to a large power. So u is always the inside item. I don't mean u is everything. No. U is just the inside part. Okay, I wish I had a red pen. I can't seem to find my red pen. Okay. So u is this inside part. This is our u. So we're going to say let u be 2x minus 5. Now, if we are letting 2x minus 5 be u, then this whole expression can be rewritten. Okay, so rewrite the original expression. Rewrite the original expression. Okay. Replace 2x minus 5 with u. Yeah, so this is going to give us y is equal to 5. Wherever there's 2x minus 5, I'm going to put u. So this is going to be u to the power 10. Yeah, so when we differentiate, so we're going to do two differentiations. I'm going to differentiate u with respect to x. This is going to give me du over dx. Okay, and then I'm going to differentiate y with respect to u. This will give me dy over du. Then I just multiply the two derivatives. Very easy. Okay, so dy over du is the derivative of this expression that has y and u. Now, when you differentiate, you multiply the power by the coefficient, and then you subtract 1 from the power. So this is going to give us 50 u to the power 9. Okay, this is dy over du. We get dy over du by differentiating this expression that has y and u. We get du over dx by differentiating this expression that has u and x. So we found dy over du. Now let's find du over dx. Du over dx is simply the expression, the derivative of the expression that has u and x. So this is going to be du over dx is going to be the expression that has u and x is 2x minus 5. Okay, so the derivative of this with respect to x is going to be the constant or just disappear, and here the letter will just disappear. So the answer is just going to be 2. Okay, we have dy over du, we have du over dx. Now, to get the complete derivative, we need to multiply dy over du by du over dx. Okay. This is baby stuff. Baby stuff. The real stuff will come very, very, very soon. So we said dy over dx is equal to dy over du times du over dx. Okay. Next, we have found dy over du to be 50 u to the power 9. We have found du over dx to be 2. To get the complete derivative, we just multiply these two. So we're going to get dy over dx is equal to 50 u to the power 9 times 2. These two just multiply the 50. We're going to get 100 u to the power 9. Now, remember, u was not originally there. We just brought it in, okay? And we said let u be 2x minus 5. So wherever we're going to have u, we're going to replace it with 2x minus 5. Okay, so this is going to be dy over dx is equal to 100, open brackets, 2x minus 5, everything to the power 9. That is an example of a derivative using chain rule. Okay, let's go. Let's do another question. You may be asked to differentiate. Find dy over dx of sine squared x cos x. Sine squared x cos x. Okay. So let's see. Are we able to do this? Okay, let's try. So, careful. Sine squared x cos x can actually also be written as sine x squared, and then you have cos x. Okay. Now, we need to pick our u. What is our u? The u is the complicated item. So, sine x is going to represent our u. Okay, so I'm going to select u be sine x. Okay. Then we need, so because we have identified u, we can write the original expression. We can say, let's assume the original expression was y is equal to sine squared x cos x. Then this is going now to be written as y is equal to u squared cos x. So we have two expressions, the expression for y and we have an expression for u. Okay, we're going to differentiate this expression that has y and u. Okay, is this going to work? Okay, no. Let's just use algebraic expressions. So assume y is equal to 3 x squared plus 4x plus 5, and then all this is being raised to the power 6. We'll do harder questions later, don't worry. So we're going to say let u be equal to x squared plus 4x plus 5. We can replace wherever we have this expression with u. We can say y is going to be 3 to the u to the power 6. We have an expression that has u and x and an expression that has y and u. So dy over du is going to be the derivative of this. Okay, this times that is going to give us 18. Then we're going to take one from the powers. It's going to be u to the power 5. Next, we need to find du over dx. Du over dx is going to be the derivative of this expression. This is just going to be 2x plus 4. Remember, the constant will disappear. And then we substitute. So this is going to give us dy over dx is equal to dy over du times du over dx. Then we substitute. Dy over du, we found it to be 18u to the power 5 times du over dx is going to be 2x plus 4. Okay. Let's go. So to differentiate this, chain rule couldn't work because this is a product, so we're supposed to use the product rule. Okay, but then there are questions that come in this form where chain rule actually is what should be used. I'll try and look for one. Okay, so we have dy over dx is equal to 18 u to the power 5 times 2x plus 4. So multiplying these, so I can write this as 18 so that it looks neat. This 2x plus 4 can be written in between the 18 and the u. So this is going to be 2x plus 4. And then u to the power 5. Then I replace u with what it originally was. This is going to be 18, open brackets, 2x plus 4. And then u is going to be x squared plus 4x plus 5 to the power 6. How to differentiate the quadratic expression? You differentiate each item in the quadratic. You differentiate x squared, that will give us 2x. You differentiate 4x, that will just give us 4. You differentiate 5, that will just give us 0. Okay, so that's about chain rule. Now, everything that we are from doing is small fish. The real stuff is about to start. Implicit differentiation. You can write the title. Implicit differentiation. This is the real stuff that I wanted to introduce today. You can expand, but you guys are familiar with binomial. And expanding a power of 6, how long is it going to take you? You get? Yeah, so you still arrive at the same answer even if you were to expand, but then the expansion is going to take a very long time. Okay, implicit differentiation. So pay attention to what I'm about to say. The power is not 5. The original question. Oh, 5. Okay. Yeah, thank you. So implicit differentiation. So here you are asked to differentiate. Here you are asked to differentiate something that is not there. Here you are asked to differentiate something that is not there. Okay? So you differentiate what is there. So you differentiate what is there and show that you couldn't find what you were originally asked to differentiate. Okay, so understand this. Here you are asked to differentiate something and you find that that thing is not there. So you differentiate what you find and show that you couldn't differentiate what you were originally asked to differentiate. So it's like they send you to buy Millie Meal. They give you 200 kwacha to say buy Millie Meal, okay? Then you find that all shops, the Millie Meal is done. But you know people need to eat at home and you look around for the Millie Meal, you can't find it. So the next best thing you do is, okay, let me take pictures to show that in ShopRite there's no Millie Meal, to show that in Pick n Pay there's no Millie Meal. So let me take pictures. Okay. Now, when you're done taking pictures, you realize, oh, at home they still need to eat. So you instead go and buy a Hungry Lion. Now, when you get back home, you give the Hungry Lion to your parents. And before they shout at you, you show them the picture to say, look, there was no Millie Meal, but I knew you guys needed to eat, so I bought you guys a Hungry Lion. So it is similar to that. Okay? So you are asked to differentiate something that is not there. So you differentiate what is there and show that you couldn't find what you were originally asked to differentiate. You get? So how does this work? I want us to compare two things. I want us to find d dx of x squared, okay? And I also want us to find d dx of y squared. Now, for both derivatives, we are differentiating with respect to what? So you can comment. We are differentiating. What are we differentiating with respect to? What are we differentiating with respect to? Like, what is our focus here? What is our focus here? Remember, the focus is what comes after the d. We talked about it. What is the focus of this derivative? Just mention the letter. What is the focus of this derivative? Just mention the letter. You can comment. Okay, quickly. So we are differentiating with respect to x. Understand? We are differentiating with respect to x. Now, part A is straightforward because you are differentiating with respect to x and you have an x. Part B is a bit rough. You are differentiating with respect to x, but you don't have x. Remember, you are differentiating something, but then you find that it is not there. You understand? Okay, so this is A, this is B. Let's differentiate B together. What is going to be our answer? What is the derivative of x squared? What's our answer? Quickly, what's the derivative of x squared? What is the derivative of x squared? What is the derivative of x squared? What is the derivative of x squared? Quickly. What is the derivative of x squared with respect to x? 2x. Excellent. So when you differentiate x squared, you're going to get 2x. So here, when you d dx of x squared, the answer is going to be 2x. And we finish chapter for this part. Okay? So we used the power rule. We had the coefficient of 1. We had a coefficient of 1. So this is going to be 2 times 1, that gives us 2. And then subtract 1 from the power, that just gives us x to the power 1, which is just 2x. Okay, so if we're differentiating x with respect to x, there's no problem. It's straightforward. Now, this is where it is hot. Pay attention to what is about to be done. Pay attention. So d dx of x squared, or rather of y squared, we are being asked to focus on x. But you notice we don't have any x, we only have y. Okay, they want us to differentiate x, but we don't have x, we only have y. So we are going to differentiate this y that we have found, but show that this was not what we were asked to differentiate. Okay, so we're going to differentiate y normally with, this is going to give us 2y. The same way that you differentiated x, you multiply the coefficient by the power and then you subtract 1 from the power. We get 2y. But you don't end here. You understand? You show that you don't end here. You show that what you were originally asked to differentiate was not found. Remember, it's like you're sent to buy millimil. You don't find millimil. So you instead buy Hungry Lion and take pictures that you couldn't find millimil. So whenever you differentiate y with respect to x, differentiate normally, but always add a dy over dx. Okay, so differentiate normally, but always add a dy over dx. So whenever you're differentiating a letter that isn't the denominator part, you differentiate it normally, but add a dy over dx. So this is going to be our answer for this. You get? You're going to see its applications very, very soon. This is just a small part. Okay, hopefully you guys have seen the contrast. Dx and you have x, straightforward. Dx and you have y, it's a bit funny. You differentiate normally, but then you add dy over dx. You understand? Okay, let's do a question. Find d dx, okay? Find d dx of x squared plus y squared is equal to 1. Okay, so they're asking you to differentiate this whole expression. Okay, so this is going to be d dx of x squared plus d dx of y squared is equal to d dx of 1. So the derivative of the whole thing is the derivative of the first thing, second, and the third. This is straightforward. They're asking us to focus on x and we have x. So the answer here is just going to be 2x. This is the implicit part. They're asking us to differentiate with respect to x, but we only have y. We're going to differentiate y, but show that we couldn't find the original thing. So plus 2y. Now, whenever you're differentiating different things, you should always add a dy over dx, okay, is equal to d dx of 1. The derivative of a constant is always 0. Now, the key with these questions is make dy over dx the subject. Make dy over dx the subject. Okay, so we want to make this the subject of a formula. So the 2x can cross the equal sign. So we're going to get 2y dy over dx is equal to, this was positive, when it crosses it becomes negative. So negative 2x. Making dy dx the subject of the formula, I'm going to divide both sides by 2y. This side by 2y. Okay, we are going to have dy, we're going to have dy over dx is equal to, dy over dx is equal to negative, now the 2's can cancel out, so negative x over y. Okay, so this is the derivative. And remember, I told you that the derivative actually gives us an expression for the gradient. The derivative gives us an expression for the gradient at any point. So as long as you have x and y, you can always find the gradient at that particular coordinate. For instance, they say find the gradient of x squared plus y squared is equal to 1 at 1, 1. This is how these questions would typically come. So if you are to graph this, you know this is a circle with a radius of 1. So this circle is going to be like this. Okay? And because this is a unit circle, the distance from here to here is 1, here to here is 1, 1, 1, 1, and so on. So 1, 1 is going to be here. Okay? 1, 1 is going to be here. Okay. Roughly. No. Yeah, 1, 1 is going to be there. And we have differentiated this, and the expression for the gradient, dy over dx is going to be negative x over y. We want the gradient at 1, 1. Okay. So if I plug in 1 and 1, we're going to get x is 1, so negative 1 over 1. We're going to get negative 1. Now, dy over dx gives us the expression for the gradient, meaning whatever we get after substituting is the gradient. So m is equal to negative 1. We can confirm that 1, 1 is here. To get the gradient, we draw a line that just touches the function at one point. And you can tell that the slope of this gradient, you know, gradients differ. If a gradient is like this, then it's going to be positive m. If a gradient is like that, then it is going to be negative m. As you can see, this gradient is sloping, so it's going to be negative. It makes sense. So hopefully you guys understand implicit differentiation. We're going to do 2 more questions, actually 3 more questions under implicit, so that you just cement the whole thing. And all 3 questions I'm going to do are exam questions, so pay attention to them. Pay attention, pay attention. Okay, find d dx of 2 to the power x. Please pay attention to this question. Okay, this is an exam question. Find d dx of 2 to the power x. Now, sometimes you don't even realize that you're going to differentiate implicitly. And at the end of the day, you just need to know, okay, this question is handled in this way. So pointers. Okay. Equate 2 to the power x to y. Okay. So this expression is now going to become d dx of y is equal to 2 to the power x. I haven't changed anything. All I've done is equate this to y. Okay, so equate 2 to the power x to y. Now, you need a concept that can make a power become a coefficient, because you want this x to become a coefficient. What is the only concept that can make a power become a coefficient? What is the only concept that can make a power become a coefficient? So you can comment quickly. What is the only thing that can make a power become a coefficient? What is the only thing that can make a power become a coefficient? Quickly comment. What is the only concept that can make a power become a coefficient? So logs, okay? Logs, as you know, logs, logs have that ability. So in simple terms, introduce. Now, the appropriate log to introduce is ln. So introduce ln to both sides. Now, mind you, all I'm doing is altering this. I haven't yet started differentiating. I equated it to y, I haven't yet differentiated. Then I'm going to introduce ln on both sides. You get? Introduce ln on both sides. I haven't yet differentiated. So this is, we had d dx of 2 to the power x. Okay? Like this. I equate this to y. I get d dx of y is equal to 2 to the power x. Now, I need something that can bring this x down. So I introduce ln to both sides. I haven't yet started differentiating. So this is going to give me d dx of ln y is equal to ln 2 to the power x. I haven't yet started differentiating. Okay. Now, this log is going to make this power become a coefficient. So ln is the most appropriate to work with. It is the most appropriate to work with. Okay, so that is going to be d dx ln y is equal to x ln 2. Do you see that? So this expression has been altered and it has become like this. We needed to equate it to y so that we could introduce ln to both sides. And then the introduction of the ln brings down the x and makes it a coefficient. I hope you guys are following. Now, the derivative of this thing is as good as, because this whole thing basically just represents the 2x. Remember, we've been altering 2x. So the derivative of everything is the derivative of ln y, and it is the derivative of this with respect to x. So differentiate each item individually. So this is going to be d dx of ln y. Okay, so I'm going to differentiate this, and then I'm going to differentiate this with respect to x, because the whole thing was being differentiated with respect to x. So d dx of ln y here, okay, is equal to d dx of x ln 2. I hope you guys are following. Now, if you remember properly, this is the derivative of a log, and this is product rule. So here, log differentiation, and then this part represents product rule. Okay, I hope no one is confused. Remember, I told you implicit utuma question to rakaba. So guys, saka question mo exam yen. Differentiate 2 to the power x. You equate it to y. Okay. Introduce ln. Okay. The x is going to become a coefficient. Then differentiate each item with respect to x. Now, this isn't just logarithmic differentiation. This is also actually implicit logarithmic differentiation, because if you pay attention, you have y, but you're differentiating with respect to x. So when you have y and you're differentiating with respect to x, what should you add at the end of your answer? When you have y and you're differentiating with respect to x, what should you add at the end of your answer? What should you add at the end of your answer? When you have y and you're differentiating with respect to x, what should be added at the end of your answer? Quickly comment, what do you add? I need to make sure you guys are following. Okay, quickly. So when you have y and you're differentiating with respect to x, add dy over dx. Now, logarithmic differentiation, I hope you guys remember. Okay? Logarithmic differentiation, we focus on the middle part. We differentiate the middle part and then divide whatever, so ignore the log. Okay? Differentiate the middle part and then divide whatever answer we get by the original middle part. So, what is the derivative of ln y? According to my explanation, what is the derivative of ln y with respect to x? So ln y alone, the derivative, what is it? What is the derivative of ln y alone? What is the derivative of ln y? Remember, you can relate it to the derivative of ln x. Derivative of ln x is going to be 1 over x. Now, what's the derivative of ln y? So, derivative of ln y, yes, we have one correct answer. 2 more people to try and comment. We see if you guys are following. Yes, derivative of ln y is going to be 1 over y. One more person. Excellent. Faustina, Prince, and Diana. Mwamba, excellent. Okay. So, the derivative of ln y is going to be 1 over y. Now, we are differentiating this with respect to x. You see? But we don't have an x, so we differentiate what is there and show that we couldn't find what we were originally asked to differentiate. So, you remember this is implicit, and whenever I differentiate normally, what do we add to the 1 over y to show that this was actually differentiated implicitly? What do we add to the 1 over y? What do we add to the 1 over y to show that we were not interested in differentiating y, we were just forced? So Benson, excellent. We add dy over dx. Okay, so I'm going to add a dy over dx to 1 over y. Okay, so dy over dx is equal to, now this is a product. Okay, and product, if you remember product rule, who can remember product rule? Quickly comment. What is product rule in terms of u, v, u prime, v prime? Remember, the order doesn't matter because addition is commutative. What is product rule? What is product rule? What is product rule? What is product rule? Like, what's the expression in terms of v, v prime, u, u prime? What's the expression for product rule? Who can remember? I hope you guys jobbed, eh? I hope you guys jobbed. Who can remember the expression for product rule in terms of u, u prime, v, v prime? What's the expression? Excellent. So product rule is going to be v plus u, and then u prime, and then v prime. Okay, so here we are trying to differentiate x ln x, x ln 2, so that I just write the final answer here. Now, the order doesn't matter whether you start with u or you start with v, because addition is commutative, so the order doesn't matter. Now, u is the item that appears first. X is going to be my u, okay? Then ln2 is going to be my v. Okay, so v, what is my v? Ln2. So I'm going to write ln2 plus u, my u is x, and then I'll open brackets. Now, v u prime. So I've written my v here. U prime is a derivative of u. U is x. Derivative of x is just going to be 1. So I'm just going to have ln2 plus x times v prime. Okay? V prime. V is ln2. ln2. The derivative of ln2 is going to be the derivative of 2 divided by 2. The derivative of 2 is going to give us 0 divided by 2. So we just get 0. In simple terms, the derivative of ln2 is just going to be 0. So v prime is a derivative of v, which is just going to be 0. Okay, so x times 0 is just going to be 0. In simple terms, the derivative x ln x, the answer is just going to be ln2 plus 0, which is just ln2. So dx over x ln2, we know it's a product. We've used product rule, APASO, and we found our answer to be ln2 plus 0, which is just ln2. I hope no one is confused. We're still going. I'll do another of these questions, then I'll do it faster, just so that you have the complete idea. Okay. Let's go. Okay. So we were at 1 over y dy over dx is equal to ln2. Now, we are trying to make dy over dx the subject of the formula. So we need to get rid of this y that's a denominator. So how do I get rid of this y that's a denominator? The quickest way. I'll multiply everything by what? What do I multiply everything by for me to get rid of this y that's a denominator? Let's see if you guys are following or if you can remember your algebra. What do I multiply everything by for me to get rid of 1 over y? What am I going to multiply everything by? Okay, excellent, Teresa. Yeah, so multiply everything by y. Good. So y times 1 over y, the y's will cancel out. I'll just be left with dy over dx is equal to, y is just going to attach itself to ln2. This is going to be y ln2. Now, if we look at the history of this question, we didn't have y initially. We just brought it in, okay? We didn't have y initially. We just brought it in to make our work easier. So we need to get rid of y. Recall that y represents 2 to the power x. Recall that y represents 2 to the power x. So recall that y is equal to 2 to the power x. You see that? So wherever I have y, I'm going to put 2 to the power x. So my final answer is dy over dx is equal to 2 to the power x ln 2. You see that? So for these types of questions, the original question always appears in the final answer. Remember, they asked you to differentiate 2 to the power x, and it has appeared in the final answer. Okay, let me quickly do another one here. Imagine you've been asked to find dx of 3x. Okay, so I'm going to equate 3x to y. This is as good as dx of y is equal to 3x. And then I'm going to introduce ln to both sides. This is going to be as good as dx of ln y is equal to ln 3 to the power x. Okay, the ln is going to drop down the 3. I'm going to have d dx of ln y is equal to d dx. When the x comes down, I'm going to have x ln 3. Okay, this is implicit differentiation. This is product rule. So it's a product of a log and an algebraic expression. So derivative of ln y is going to be 1 over y, but because we're focusing on x and we have y, we need to add dy over dx is equal to, this is a product, okay? So product, we quickly differentiate this part. So x ln 3, this is my u, this is my v, okay? So v plus u prime, v prime, okay? My v is going to be ln 3 plus my u is going to be x, okay? The derivative u prime, the derivative of x is going to be 1. The derivative of v, which is ln 3, ln 3 is actually a constant, it will give us 0. So the derivative of x ln 3 is just ln 3. So derivative of x ln 3 is just going to be ln 3. Then I multiply everything by y to get rid of this. I end up with dy over dx is equal to y ln 3. Then replace y with the original item. We say dy over dx is equal to 3 to the power x ln 3. You finish. Okay, easy stuff. So you see, I've done it in a very short period of time. It just looked lengthy because there are some parts that needed to be explained to you guys. Okay, let's go to the next question. Let's go to the next question. Let us go, let us go, let us go. Find d dx of x to the power sine x. Find d dx of x to the power sine x. Now, before we go further, what mnemonic do we use when we are differentiating trigonometric ratios? What mnemonic do we use when we are differentiating trigonometric ratios? The same mnemonic is used when we're looking at sec and cosec. The same mnemonic helps us remember that tan is made up of sine and cos and the like. What mnemonic do we use when we are differentiating trigonometric ratios? What mnemonic do we use when we are differentiating trigonometric ratios? Okay, state cancel. Excellent. Excellent, state cancel. Good, you guys can remember. Yes, so differentiating sine is going to give us cos. State concile. You concile finshi. Concile tefila babon shabana kashi kuli power dashani. Can concile, I don't know. Alright, so state cancel is a mnemonic that we use. Now, this is not so different with the derivative of x, or rather 2 to the power x. So, I'm going to equate this to y and then introduce ln. Good. So this is going to be d dx. This is going to be y is equal to x to the power sine x. Okay, then I introduce ln on both sides. This is going to be d dx of ln y is equal to ln x to the power sine x. Okay, let's go. This is sweet stuff, man. Let's go, let's go, let's go. This log is going to make the sine x drop. So we're going to have d dx of ln y is equal to sine x ln x. You see that? Easy, easy, easy stuff. If you pay attention, this is an implicit part, this is a product. Okay, so this is going to become d dx of ln y is equal to d dx of sine x ln x. Okay, this is going to give us 1 over y, obviously 1 over y, but because we're differentiating implicitly, we add dy over dx is equal to, this is a product. Okay, so this is going to be my u, this is going to be my v. Okay, so I'm going to write, you know the formula is what? V plus u, u prime, v prime. So I'll write my v, which is going to be ln x. I'll put this in brackets, plus I'll write my u, which is going to be sine x. I'll open brackets. Okay, then I'll put the derivatives inside the brackets. Here I'm going to have u prime. That is the derivative of sine. What is the derivative of sine? What is the derivative of sine according to the mnemonic that you've just stated? What's the derivative of sine? What is the derivative of sine? What's the derivative of sine according to the mnemonic state council? What is the derivative of sine? What is the derivative of sine? So, the derivative of sine is going to be cos according to the mnemonic state council. Derivative of sine is going to be cos, so I'm going to put cos x here. Here, what is the derivative of ln x? What's the derivative of ln x? What is the derivative of ln x? What's the derivative of ln x? Logarithmic differentiation. So hopefully you guys are now seeing the importance of that introductory session that we had, because product rule is being applied, logarithmic differentiation is being applied, general power rule is being applied. So the derivative of ln x is going to be 1 over x. Now careful, these x's can't cancel out to a part. I'll say that again. These x's cannot cancel out. You get? These x's cannot cancel out. So this is going to be written as 1 over y dy over dx is equal to, I prefer to write this as cos x ln x plus, this is going to be 1 over x sine x, because the x's can't cancel out. Okay, then I'll multiply everything by y. This is going to leave us with dy over dx is equal to y cos x ln x plus 1 over x sine x. Then recall that y was x to the power sine x. So final answer is going to be dy over dx is equal to x to the power sine x, open brackets, cos x ln x plus 1 over x sine x. That is how you differentiate implicitly. Okay, one more question, and then we can end the session. One more question so that you quickly have your homework question. One more question. Okay, one more question. So you can write the title, differentiating inverse trigonometric functions. So differentiating inverse trig functions. Differentiating inverse trig functions. So we will be looking at the derivatives such as find d dx of x, of cos inverse of x, or d dx of sine inverse of x. Now, in mathematics, they won't always write it as cos inverse or as sine inverse. What is the alternative way of writing cos inverse? What's the alternative way of writing sine inverse? Quickly, we can comment. What is the alternative way of writing cos inverse in terms of just letters? What's the alternative way of writing sine inverse? So that if they do bring it in that form, you are not confused. So cos inverse is going to be written as arc cos. Okay, arc cos. This is going to be arc sine. You see that? Arc cos, arc sine, arc tan. You understand? So this question could actually come as find d dx of arc cos of x, or find d dx of arc sine of x. Hopefully you guys are following. Okay. Now, I'm going to teach you this, and then this other one is going to be your homework. Pay attention, okay? Pay attention. So find d dx of cos inverse of x. Now, this also falls under implicit differentiation. Okay, so pointers. Equate the expression to y. So equate the expression to y. Next, make the cos inverse cross the equal sign. Make the cos inverse cross the equal sign. Okay. Then differentiate each item with respect to x. You understand? Then get rid of y. Now there are two steps involved in getting rid of y. The first step is use sine squared y plus cos squared y is equal to 1. Okay, and make sine y the subject. The number 2, recall that y anyway, all this will make sense. Recall that cos y is equal to x. You're going to see all this. So take a screenshot of this. You need it. So equate the expression to y. Make cos inverse cross the equal sign. Actually, let's do this. Let's solve this question while referring to this pointer. Let's solve this question while referring to these pointers. Okay, so we've been given the question. Find d dx of cos inverse of x. The first pointer was equate the expression to y. So this is as good as d dx of y is equal to cos inverse of x. Okay, so you need to know the questions that you need to equate to y. These that we've done. Next, make the cos inverse cross the equal sign. Now, this may be a bit tricky. Imagine you have cos theta is equal to 1 over 2. Okay? To make theta the subject of a formula, cos is going to cross the equal sign. Okay? So when this cos crosses the equal sign, I'm going to have theta is equal to cos inverse of 1 over 2. Now, if cos can move from here to this side, it means the reverse is also true. It can also go back. If this cos goes back, I'm going to still get cos theta is equal to 1 over 2. So cos can cross the equal sign, and the only thing that changes is whether it's going to have an inverse or not. Okay. So make the cos inverse cross the equal sign, and I've shown you that it's possible to take it back to where it was. So when this cos crosses the equal sign, I'm going to end up with d dx is equal to, the inverse will disappear. This is just going to be, d dx of cos y is equal to, the x will remain alone, x. Yet, look what happened. cos can cross to become cos inverse. The inverse can be taken back to just give us something that is alone. Okay. Now, this means differentiate this part, differentiate this part. So this is going to be d dx of cos y is equal to d dx of x. Now, this is implicit differentiation because we're differentiating with respect to x, but we have a y. Here, it's straightforward. What is the derivative of x? Quickly comment. I just need to make sure everyone is following. What's the derivative of x with respect to x? What is the derivative of x with respect to x? Just make sure you guys are following. What's the derivative of x with respect to x? Excellent. The answer is 1. So the right hand side, I'm going to put 1. No need of putting dy over dx because everything is straightforward. Now here, what is the derivative of cos y with respect to x? Remember, use the mnemonic state cancel. What is the derivative of y with respect to x? Like the full answer. What am I going to have? Pay attention to the sign. Benson is not 1 over x. No. It is just x. Derivative of x is just 1. Okay. What's the derivative of cos y with respect to x? So negative sine y. Now, careful. It's not just negative sine y. This is an implicit type of differentiation. So it's not just negative sine y. Excellent. Negative sine y dy over dx. Remember, implicit, you have to show that what you were asked to differentiate is not actually there. So this is going to give us negative sine y dy over dx. You see that? So I've differentiated this part, I've gotten 1. I've differentiated this part, I've gotten negative sine y dy over dx. Okay. Now, make dy over dx the subject of the formula. So I'm going to divide both sides by negative sine y. By negative sine y. So this is just going to give me dy over dx is equal to, now this negative can be taken on top. I'm going to have negative 1 over sine y. Let's go back to the pointers. The pointer said equate the expression to y. Okay? Make cos inverse cross the equal sign. It did. Here. Where? Here. Okay? Then differentiate each item with respect to x. We've differentiated each item with respect to x and we've ended up with this. Okay? Next, get rid of y. Now, there are 2 steps involved in getting rid of y. Use the identity sine squared y plus cos squared y is equal to 1. Make sine y the subject of the formula. So for now, let me use the identity. We said use the identity sine squared y is equal to, or rather plus cos squared y is equal to 1. I need to make sine y the subject of the formula. First of all, cos will cross. I'm going to get. Now, this looks like you're not getting rid of y, like you're just complicating the whole process, but it's part of everything that should be done. Sine squared y is equal to 1 minus cos squared y. Okay? Making sine y the subject of a formula. How do I make sine y the subject of a formula? How do I get rid of this square on top? How do I get rid of this square on top? How do I make sine y the subject of a formula? I don't want sine squared y, I just want sine y. How do I make sine y the subject of a formula? How do I make sine y the subject of the formula? Okay, so I'm going to square root both sides. I'll square root this side, I'll square root this side. Now, this can be simplified further, okay? Because, so this square root will still be maintained. In simple terms, I'm going to end up with sine y is equal to square root of 1 minus cos squared y. Okay. So wherever I have sine y, I'm going to replace it with 1 minus cos squared y. Remember, I had negative 1 over sine y. So I'm going to replace this sine y with this. I hope you guys are following. This is going to give me dy over dx is equal to, don't forget there was a negative 1 on top, divided by, below I had sine y, and I'm replacing sine y with square root of 1 minus cos squared y. So this is going to be square root of 1 minus cos squared y. You see that? How do we get rid of y? Number one, use this identity and make sine y the subject of a formula. So I've done the first thing. Okay? I now do the second thing. Recall that cos y is equal to x. Let's look at the original question. Wherever I have cos y, remember we had y is equal to cos inverse, the cos crossed. So wherever I have cos y, I can replace it with x. This is a very important point. Recall that cos y is equal to x. Meaning, wherever I have cos y, I should put x. I think let me just start this on a fresh page. So I have dy over dx is equal to negative 1 over square root of 1 minus cos squared y. Okay? And we can recall, so recall that cos y represents x. Understand? Meaning, if I have cos y, I'll just put x. But if I have cos squared y, it means I've squared this part. I should also square this part. So cos squared y is going to represent x squared. I hope you guys are following. Recall that cos y is equal to x. So wherever I have cos y, I can put x. Now this cos y has been squared, meaning the x should be squared as well. So I'm going to have dy over dx is equal to negative 1 over square root of 1 minus, where I have cos squared y, I can replace cos squared y with x squared. So minus x squared. You see that? And I'm done. In an exam, they will tell you to say, show that dx of cos inverse of x is equal to negative 1 over square root of 1 minus x squared for what? Negative 1, blah, 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 blah. This is how such questions come. Okay, let me see if I have an example so that I show you guys. Let me see. I hope I have such a question. Okay, just relax. I show you how this question would come in an exam. Let me show you. Do I have it anywhere close by? Do I have it? Okay, just relax. Okay, it's not here. Just relax. Okakasanga, each and everything that we've done, you'll find them. So make sure you revise each and every part properly. Revise these things very, very, very well. Revise them. I can't seem to identify that paper. I can't seem to find it. Sad. I was hoping I would show you guys. I can't seem to find it. Yeah, okay. So your homework. Show that. No, in fact, show. I won't even tell what it looks like. Find dx of sine inverse of x. That is what I want you to find. Find d dx of sine inverse of x. Yeah. Find d dx of sine inverse of x. Yeah, so that's your homework question. All the best, guys. We shall have the next session communicated in good time. Please revise, begin revising even as you're learning these new things. Okay, have a good day. Take care.